probability theory as an extension to logical reasoning. Probabilistic modeling provides a principled foundation for designing machine learning methods. Once we have defined probability distributions corresponding to uncertainties of our data or problem, it turns out that there are only two fundamental rules, the sum rule and the product rule. Recall that P of x and y is the joint probability distribution of the two random variables x and y. The distributions P of x and P of y are the corresponding marginal distributions, and P of y given x is a conditional distribution of y given x. Given the definitions of marginal and conditional probability for discrete and continuous random variables, we can now present two fundamental rules in probability theory. The first rule is the sum rule. Let psi be the state of the target space of a random variable y. Let P of x be the marginal distribution of a random variable x. Then P of x is the sum over all y of P of x and y if y is discrete, and the integral over all psi P of x and y dy if y is continuous. This means that we sum out or integrate out the set of states y of the random marginalization variable y. The sum rule is also known as the marginalization property. The sum rule relates the joint distribution to the marginal distribution. Let's consider an example. Consider the set of cards, each with a shape and a color. The number of cards of each type is given in the table below. Use the sum rule to determine the probability of drawing a red card. So we see we've got a column of red cards. Some of them are squares, some of them are triangles, some of them are circles. So the probability of drawing a red card is equal to the sum over all of the shapes of the probability of drawing a red card with each individual shape. So the probability, so we have here, then we've got the sum of the probability of red in square, plus the probability of red in triangle, plus the probability of red in circle. There's 700 items in this data set. So the probability of red in square is 20 over 700. The probability of red in triangle is 30 over 700. The probability of red in circle is 50 over 700, which is 1/7. The second rule, known as the product rule, relates the joint distribution to the conditional distribution through the formula P of x and y equals the probability of y given x times the probability of x, where the probability of y given x is a conditional probability. Product rule can be interpreted as the fact that every joint distribution of two random variables can be written as the product of two other distributions. Those distributions are the marginal distribution of the first random variable, so P of x, and the conditional distribution of the second random variable, so P of y given x. However, we'll note that the ordering of x and y is arbitrary, which means that the probability of x and y is the same as the probability of y and x, which means the probability of x and y is also equal to the probability of x given y times the probability of y. Consider a set of cards with a shape and a color. The number of cards of each type given in the table below. We know that the probability of drawing a red card is 1/7. Given that, what is the probability of drawing a red triangle? Well, we know the answer to this because we know there are 700 cards in the deck, and 30 of them are red triangles, so the answer should be 30 over 700, or 3 over 70. But if we want to take advantage of our previous formula, we'll see that the probability of drawing a red triangle is the probability of drawing a triangle given that your pick was red times the probability of picking something that was red. We know that the probability of picking something that was red is 1 in 7. We also know the probability of picking a triangle, given that we picked something red, is 30 of this total 100. Over 100 times 1/7 is 3 over 70. Of course, we could have done this directly, but we want to illustrate in this example that we can use this conditional probability rule. In machine learning and Bayesian statistics, we're often interested in making inferences of unobserved latent random variables, given that we have observed other random variables. Let's assume we have some prior knowledge, P of x, about an unobserved random variable x, and that we have a relationship between x and a second random variable y. So we have a relationship of the form P of y given x. If we observe y, we can use Bayes' theorem to draw some conclusions about x given the observed values of y. Bayes' theorem states the probability of x given y is equal to the probability of y given x times P of x divided by P of y. This is a direct consequence of the product rule we saw in the preceding slide. If we know that the probability of y given x times P of x is equal to the probability of x given y times probability of y, we can simply divide through by the probability of y and get that the probability of x given y is equal to the probability of y given x times the probability of x divided by the probability of y. In Bayes' equation, P of x is what we call the prior. It encapsulates our subjective prior knowledge of an unobserved latent variable x before observing any data. We can choose any prior that makes sense to us, but it's critical to ensure that the prior has a non-zero PDF or PMF on all plausible x, even if they're very rare. The likelihood, probability of y given x, describes how x and y are related. And in the case of discrete probability distributions, it is the probability of the data y if we were to know the latent variable x. Note that the likelihood is not a distribution in x, but it is really just a distribution in y. All that changes is y. We call the probability of y given x either the probability of y given x or the likelihood of x given y, but we never refer to it as the likelihood of y. So keep that in mind. The posterior, the probability of x given y, is the quantity of interest in Bayesian statistics because it expresses exactly what we are interested in. That is, what we know about x after having observed y. The quantity P of y is the marginal likelihood, or the evidence. You'll notice that it's the integral of P of y given x times P of x dx, or the expected value of P of y given x. We haven't discussed that yet, but we will in a later on in this video. Here's another example. We know that 30% of all spam emails have the word release in them. Only about 0.8% of all ham emails have the word release in them. Of all emails sent, about 40% are spam. An email is received with the word release in it. How likely is it to be spam? Well, let's first look at the probability of an email being ham. So if it's not spam, it's ham. And if 40% of all emails are spam, then 60% have to be ham. Now, what is the probability that an arbitrarily selected email has the word release in it? Well, we have to look at the probability that an email has release in it given that it's spam, times the probability of spam, plus the probability that an email has the word release in it, given that it's ham, times the probability of ham. So plugging in the numbers we have, that's 0.3 times 0.4 plus 0.008 times 0.6. Now we're in a position to find out the probability that an email is spam, given that it has the word release in it. So the probability of spam, given that it has the word release in it, is the probability that it has the word release, given that it's spam, times the probability of spam, divided by the probability of release. We've calculated the probability of release already. The probability of release given spam times the probability of spam is 0.3 times 0.4, which means that a randomly selected email that has the word release in it has about a 96.1% chance of being spam. One last example. A doctor suspects a patient has one of three diseases, D1, D2, or D3. Two tests are given, and based on the results, we're going to make our diagnosis. Based on 10,000 previous patients, the distribution of the results are shown as follows. Depending on whether you get two positives, a positive, a negative, a positive, or a negative, we have a different distribution of what diseases a patient might get. So for example, if we want to look at a patient who has two positive tests, about 2,100 of them have disease 1, about 400 have disease 2, and about 500 have disease 3. So let's take a look at the probability that a patient has disease 1, given that they got two positive tests. So the probability of having disease 1, given two positive tests, is the probability of having two positive tests, given that you have disease 1, times the probability of disease 1, divided by the probability two positive tests, given that you have disease 1, times the probability of disease 1, plus the probability of having two positive tests, given that you have disease 2, times the probability of disease 2, plus the probability of having two positive tests, given that you have disease 3, times the probability of disease 3. Figure each of these out. The probability of two positive tests, given that you have disease 1, is 0.656. Probability of disease 1 is 0.3215. We get those two numbers by, there's 10,000 people here, so probability of disease 1 is 3215 divided by 10,000. And the probability of having two positive tests, given that you have disease 1, is this 2110 divided by 3215. Similarly, we have the probability of two positive tests, given that you have disease 1, times the probability of disease 1, plus the probability of two positive tests, given that you have disease 2, times the probability of disease 2, plus the probability of two positive tests, given that you have disease 3, times the probability of disease 3. Simplifying, we get 0.2109 over 0.3012, or about 70%. This makes a lot of sense, because if we had two positive tests, it seems much more likely that we have disease 1 than either of the other two diseases. I've gone ahead and calculated the probabilities for the other types of the other choices here. Make sure that you can get each of these answers.